Since it is already 5:09, so it's already 9 minutes after the scheduled time, and no one is joined till now. And so I am going to start, and I will upload the video in the YouTube. So if anyone have any queries, they can comment there or can email me later. So I am Shripan Mandal. I am working as a research scholar at IIT BHU, and I am conducting this live sessions for last 10 weeks, and this is the 11th week in which I am going to discuss about the Lienard Jones Potential, for which we will going to calculate the fluctuation in kinetic energy as well as potential energy when we are considering it to be without the thermostat, and if it is with the thermostat, then we will consider the total energy as well as the potential energy, because in that case kinetic energy will be constant. So we will go into the details that what is thermostat and what is the effect of using that while doing the simulation. So before moving on to those questions related to Lienard Jones potential, we have another question to look after, which is this question. The question is suggesting that there is a quantity, say LLX, which is equals to 30, and we have to calculate the values of x, y, and z, which are defined as the modulo as these equations. So we have x equals to modulo 26.06 d0, that means the double precision, which has to be divided by the LLX. So whenever we started with this LLX to be 30, then you see that in the modulo operation, the value on which LLX is operating is a float or double precision one, but the LLX is given as the integer, so it will not give you the right value. So what we have to do is we have to convert the LLX value of 30 to be the double precision, or if not double precision, then it has to be converted to float, so that the both of the numbers will be in the same type, and therefore the modulo operation will be act properly. So you see in the first that x equals to modulo 26.06 d0, and it will be divided by LLX. So it's like 26.06 is divided by 30.00, so that means the modulo will give us the remainder when we are dividing this number by another number. So here the remainder will be the 26.06, since it is less than 30. So what we are going to get is 0 into 30 plus 26.06, so it gives us the 26.06 to be the correct answer for this first question. So then if we are going to calculate y, then you see that 30.05 is divided by 30, so it will give like 1 into 30.00 plus 0.05 as the remainder. That means the modulo operation will give you the value of 0.05. so that is here, and that 5 into 10 to the power minus 2, and z will be you see in the z operation, the value which is going to divided by 30.00 is minus 0.04. so you have to remember here that if there is a minus with the value which you are going to divided by the LLX, then the operation will be like 29.96. that means if you add this 29.96 plus 0.04, then it will give you the value of 30.00. so if there is a minus, then it will be this type of a operation when we are using the modulo operation. Okay, so let's move on to the next question. So we have to do a molecular dynamics simulation, which is a well-defined or well-known problem. So we have to take total of 13 into 13 into 30 13 particles, that means 2197 particles in a 20 into 20 into 20 box with dt being 0.005. so that means you are starting or running an iteration in which each of the time step has to be defined as 0.005, and you have to calculate the molecular dynamics simulation for a Lienard Jones potential. So Lienard Jones potential will have this kind of a form, is 4 into epsilon sigma by r to the power 12 minus sigma by r to the power 6. So you have this potential given, and you see there are different parameters which have given their values, and then you have to run the simulation for 20,000 iterations without thermostat. So what does it mean by without thermostat? So basically, when the iteration is going on, so at each time step there will be increment of the temperature, and that will increase the kinetic energy itself. Now if there is no thermostat, that means the temperature of the ensemble is not a constant, rather it is increasing. But if we are calculating it with thermostat, that means the temperature will be constant, therefore the kinetic energy will remain constant. And if potential energy is fluctuating, that means the total energy will fluctuate in that case. But without thermostat, it is like a NVE system rather than NVT system. That means the number of particles, volume of the system, and the total energy of the system will remain constant in this case, but potential energy and kinetic energy are free to fluctuate around certain values, so that the total energy will remain constant. So in this case, we have to calculate the potential energy and kinetic energy's fluctuation around certain values, which we are going to evaluate by solving or by running the simulation. So we have certain high integers like z, and 4 z's, and then we are going to define the length of the box in each dimension, which is Lx, Ly, Lz, each one of them to be set to be 20, and the total number of particles is 2197, and kBt is taken to be 1, and this is for simplification of the simulation. And then Ni is 20,000, that means the total number of iteration, and mass is given to be 1, and the other values which have been given in the question are this. So then what we have to do is we have redefined some parameters so that they have to be calculated at the beginning of the code, and at each iteration we don't need to calculate them again and again. So it will speed up our calculation or simulation time. So then again this fc1 and fc2 is again some redefinition, and then we have some the difference in modified potential at RC is that point at which the classical to quantum limit will be incorporated. So then we have some arrays, and each one of them will be one-dimensional arrays having the total number of elements within that to be 3 times of the number of particles. And then what happens is there is some definition or definition of different parameters used in this program. So so initially we have defined a module in which we have defined all the parameters with their values as well as their types. So after that we have to write the main program, which is a program MD, molecular dynamics, and then there we have used the modulo, which is sim_para, which have been defined here. And then we have considered that implicit none, so no parameters have been given and type implicitly, rather we have to given all the types to all of the variables explicitly, so as we done in all of the Fortran codes. So after that what we have to do is we have to run a random number initialization module, which is ran1. We are going to look at this ran1 at a later time, that how it is going to calculate the random numbers. So you see that Lx, Ly, Z have been given the values of 20, and then we have just convert them to floats, that means 20.0, and then see we have called two subroutines. One is position initial positions and velocity underscore int. So initially we have to give all of the particles their initial positions and initial velocity, and those two operations has been done in two separate subroutines. We can do this in this main program also, but that will make the program to be hazy and less readable. So therefore we have used the subroutine. Okay, so then after that we have opened a file which is energy and thermostat, that means without thermostat, and again also if we consider the thermostat, then the file name can be changed accordingly. So after that what we have done, that we have used the total number of loop over the total number of iteration, and if mod k by 100, that means if my number of iteration is divided by 100, totally divided by 100, that means the module will give me 0, that means the remainder is 0 if it is totally divided. Then at those points I am going to write the k value. It will help us to find out how much of the iteration has been run already. So let's say it is it will print like 100, 200, 300 in this way. So after that it will call another subroutine which is the position update. So in this subroutine what we are going to do is we have to update the position of those particles as the simulation is running. So starting from the initial positions given in the subroutine called position init. Okay, so after that we have to write all the variables like dk, that means the float. So that is the in position, sorry, that is the time step or the iteration step, and then we have to write at each of this at each of these iteration step we have to write the total the potential energy per unit per particle, kinetic energy per particle, and the total energy per particle. So this is the main program, and in this main program you see that we have used ran1, which is a function kind of thing, and then we have to use three other subroutines. One is position init, velocity init, and position update. So we have to look for these three subroutines as well as the ran1 function at the latter line of the codes, so that we have to. Okay, so let's move on to the next page. So in this you see that we have the subroutine like position update. So in this subroutine also we have used the module in which all of the parameters have given their values, and then the other parameters which have not been defined in the module same para, they are defined here, and then how to update the position. So this dt2 by 2, this is a redefinition of this half dt square. Okay, so then what I have to do, that do I equals to 1 comma 3p, that means it is hovering over all the particles in the simulation box, and then it is going to calculate or update the positions like 3i minus 2, 3i minus 1, and 3i. So that means that if you are tracking the value 1, then it will be like 3 minus 2, that is position of the 1. So what we have is total number of particles is like, since this is a 3D box or 3D simulation, so that means 2197 particles have been taken, and basically what happens that 3 into 2197 particles have been taken. So instead of making it a 3-dimensional array, we have make it as 1-dimensional array in which the first element will be the x component of the position as well as the velocity of the first particle. Second element will be the y component of position and velocity of the first particle, and third will be the z component of the velocity and position of the first particle. So in this way the array has been defined here. So this position 3 into I minus 2, that will be like the x component of the position, okay, x component of the position of the first particle. So likewise, if you calculate the np, that means the position x component of the 2197th particle, and then this way the positions will be updated, and after that we have to calculate the remainder, while it will be divided by LLX, LLY and LLZ. Those are the diploads of the 20, right, which is the dimension of the box at each of the directions. So after that we are going to calculate the forces, and those forces have been calculated here, and then also we have two loops going on here, in which we are going to do is you have, for a particle you have the nearest neighbors, and you are going to calculate the potential energy using the nearest neighbors only. So how do you going to define the nearest neighbor for a particular particle? That will depend upon the distance between them, right? So in this way, you see here, if absolute x is greater than equals to lx2, so what does it mean by lx2 here? Lx2 is defined like this. So let's say you have a box of 20 and you have the middle point at 10, and then it is saying that if the difference between the two particles for a particular particle is greater than that half of the box length, then we are going to redefine the distance between them as this, or if it is not greater than that, then it is okay to be x1 minus x2, y1 minus y2 and z1 minus z2. So in this way we are going to calculate the distance between those two particles, and then we are saying that okay, if the distance between those two particles is less than equals to RC, which is a critical value of the distance, then we are going to calculate this LJ factor, and then we are going to add. So this is the potential energy, okay. So after that, all in the similar fashion we are going to calculate the force also, and then we are going to update the force, the components of the force in different directions for each one of those particles, and then we will close the if loop, and successively the do loops. Then we are going to calculate the acceleration from those force which we have already calculated. So we have position, we have acceleration now calculated from force. So what we have to do is we have to calculate the velocity or update the velocity. How we are going to do that? So basically here you can find out these formulas in the lectures given by the faculties, I think Dr. Pushenjit Ghosh, and so after that we are going to update the velocities for each of the components for each of the particle, and then we are going to calculate the average of those in each of the direction, and then the kinetic energy will be calculated in this fashion. So after that, this has been defined as half mass into Ke, and then potential energy is Np, forces in force. So this way kinetic energy, potential energy and force has been calculated. So after that, you see here the thermostat has been used. So whenever we are using the non-thermostat condition, then we have to just comment out this portion, okay. So what it actually does is it is trying to make the kinetic energy or make the kinetic energy in such a way that it will remain constant throughout the simulation. But if we are not using this part, this thermostat part, then what will happen, that kinetic energy will keep changing, potential energy also keep changing, but the total energy will remain constant, and that's how the potential and kinetic energy has to be changed. But when we are using or decomment this section, it will give us that okay, kinetic energy will remain constant throughout the simulation, not from starting but after certain points, let's say 100 simulations or 100 iteration. So after that kinetic energy will remain constant. So therefore if potential energy is going to change, the total energy will has to be changed. Okay, so without thermostat what will happen, that your n, the number of particles, the velocity the volume of the system, and E, the total energy of the system, will going to remain constant. But if we are using the thermostat condition, then kinetic energy will remains constant, but since potential energy is fluctuating, then your total energy cannot be constant. And by thermostat we mean the temperature of the system will remain constant, that therefore the kinetic energy will remain constant throughout the simulation. So this is the difference between without thermostat and thermostat. So for thermostat you have NVT system where the temperature is constant but total energy is not constant, but without thermostat you have NV system where temperature is not constant, therefore kinetic energy is not constant but the total energy is constant. Okay, so this is the subroutine where the position as well as the velocity has been updated. Okay, so now we have the algorithm in which we are updating the position as well as the kinetic energy, but but we have to initialize first the position as well as the velocity of the particles. So how we are going to do that? So we have two other subroutines, right? So you see, again we have used the module sim para, and then we have initialized the position in this way, that we have a function which is generating random number, and then we are saying that we have a box like 0 to 20, so the position will be in between 0 to 20. So we have this ran1zzz, which will define or which will generate a random number which will be 0 in between 0 and 1, and then we are just multiplying that with 20, so it will give a random position or random number which will be in between 0 to 20. So in this way we have position 1 1 2 3, that means we have x y z component set for the first particle. Okay, and after that I equals to 2 to np, that means we have first particle set at this point, and then what we are going to do, that we have to check for the non-overlapping condition. So how are we going to do that? So basically for I equals to 2 to np, we have again given this position array elements, and then what we are going to do, we are going to calculate the distance, the difference between each one of the components for each of the particle in this different directions, and then we are going to redefine those r1 r2 r3 in this way, and then we are going to find out the distance between those two particles, and if it is less than equals to sigma, then we will go to this 11. Okay, so that means we are not going to consider that particular random number of set, because in that case there is the overlapping condition matching and we don't need to do that. Okay, so if overlapping condition is not there, that means distance is greater than sigma, then we are going to take that particular position initialization. Otherwise we will skip that particular step in which we have defined the initialization, because then the particles will overlap with each other and we don't require them to overlap. Okay, and then what we have done, there's initial position has been written in a particular file in this way, that means the x, y and z coordinates for a particular particles. Okay, so it will write all of the position things for each of the particles in this fashion. Also similarly we have the velocity initialization particle thing, in which is initialize the velocity in this way, that you have a velocity constant which is defined as this, that is square root of 12 kbt, and then what you are trying to do is you have a random number which will be around 0 to 1, and you are just negative taking a negative of that, is 0.5 is subtracting from that. That means you have all the velocities set to be from minus 0.5 to plus 0.5. Okay, and then you have calculate the average velocities in each of the direction, and then those average velocities are basically the velocities when we have divide the total velocity in each of the direction by the total number of particles, and after that we are going to at each of for each particle we are going to redefine the average velocities in this way, and then we have defined all those velocity arrays in a file at right initial velocity dot dat. Similarly for the as similar for the position. Okay, so then finally we have to look at this function in which the random number generalization is can be done. So I'm not going to depict or in details in this. So this is a very standard form of a function which will generate the random number. Okay, so this has to be used. So okay, just a second. So I hope all the algorithms are now clear to everyone. So I am going to look at the values what I have given here. Okay, so you see we have this. You see first the second one will be the potential energy, third one will be kinetic energy, and the fourth one will be the total energy. Okay, so now we are going to plot it. So for non-thermostat condition we have to find out the fluctuation in kinetic energy and potential energy. Okay, so this will be the potential energy which will be around minus 2.225, and this will be around 2.51. so if we look at the questions here, so you see this will be minus 2.25 and this is 2.55. so not exactly the correct answer here, but this is around our estimated values, right? So this will be the correct answer. And if we find out the similar thing for with thermostat, then we have to find out the fluctuation of the potential energy and total energy around some values, right? So if we look at this graph, so this is the potential energy and this is the total energy. You see this will be around minus 5.165 and this is minus 3.645. okay, so if we look at this, so this will be so this will be around this, right? Just a second. Yeah, so this will be the correct answer. So that's all for today's lecture. So no one has joined and the class has been finished, so there is no interaction at all, but I hope it will be helpful for all of them. We are going to submit the assignments in this in this year, because I am solving the assignments for the previous year. So thank you very much, and next Sunday I will deliver the last class in which I am going to show the way to solve the assignments given in the previous year for the 12th week. Okay, so thank you very much everyone, and see you on next Sunday.